Welcome to the 24th IFS seminar. Today we are happy to welcome Vardan Bardakhchyan from the Ali Khanyan National Science Laboratory. He is a researcher there. He is a mathematical economist, and he will talk about the game theory, bargaining theory. And well, we are very happy that you are here, and then the floor is yours, Vardan. Please start whenever you're ready.
Thank you very much. Thank you for this opportunity. First of all, I would like to say two words about this presentation in general. So this is the work we have done with my supervisor, Vardan. He is hearing us now. So it is our unpublished work. We haven't yet published this work. This is our second attempt to address bargaining problems. The first one was about ultimatum bargaining. So in general, this is a concise form of the paper we wrote. One thing I would like to mention, that maybe the mathematical part of this work is not that hard. So I'll keep things as simple as they indeed are. And let me start the talk. First of all, I'll like to talk about the Pareto-optimality concept, what it is. It is more general than a bargaining problem, or more general even in game theory rather than game theoretical problems. Then I'm going to talk about bargaining in general. What is it? What is bargaining problem, and what is the solution to bargaining problem? What we understand about solving bargaining problem. I will talk a little bit about Nash general solution, axiomatic solution, and the last part will be devoted to our approach to solving the bargaining problem based on famous psychophysical law called Weber-Fechner law. Let me first start about a little talk about the concept of Pareto-optimality. Whenever you solve an optimization problem of one sort, constraint or not, that doesn't matter, you have a function which you maximize or minimize. So there is one function, one goal. What can be said if you had more than one goal? This is where the Pareto-optimality concept starts to emerge. Whenever you have two conflicting goals and you try to maximize them both, so you have two objective functions like it is written here, or U1 and U2 on some region, on some predefined region, but these are conflicting goals. It means that when you maximize this goal, you may somehow deviate from the extremal points, from maximum point, desired point for the second goal. So maximizing this will, at some point, will mean minimizing this one. So how to choose the best option? One way to do it is, of course, you can combine these two functions with some weights, thinking that this will exactly match what you want. However, before doing that, there is a general concept which is called Pareto-optimality, and here what is it about? So the Pareto-optimal solution to this problem is a point when there is no other point better than this, in a sense that when you try to make U1 bigger, you in that case lessen U2, or when you try to make U2 bigger, closer to maximal point, you so lessen U1. So further maximizing one of the functions is costing you further deviating from your goal in the other function. The precise definition is given here, so it is no other point which you can keep the level of one of the functions at least the same while making better off for the other function. Let me just give geometric interpretation of Pareto-optimality and what is Pareto frontier. Pareto frontier consists of all Pareto-optimal points. So let me give an example, just a geometrical example to understand the concept more precisely. So we had two functions, u1 and u2. So it is this graph is in the space u1, u2. You can see, can I use a drawing tool here? So if I draw something like this, you will see it, yes?
Yes.
Yeah. In this graph, you can note that whenever I try to make u1 better, so I like going to this point, it will make u2 worse. So I will deviate from the maximum of u2 I can achieve in general. So in the same way, if I try to make u2 better, so I'll try to go up, that will cost me with the less u1. This is the general concept of Pareto optimality. So all these points here on this graph are Pareto optimal points. To show a little bit difference between the previous graph, so in this case, A is not Pareto optimal because you can go either you can keep u2 and make u1 better, or you can keep u1 and make u2 better, or you can even make both of them better off. Obviously, the point A is not a Pareto optimal point. Point B is indeed Pareto optimal, and it is for sure better than A because in both goals, so in both objective functions, it is better than point A. So in some sense, Pareto optimal frontier or Pareto frontier is the best options you can achieve, best without regard which goal you prefer more than the other, which goal is more valuable for you. Why we started with this Pareto optimality concept? Because bargaining problem is indeed and game theory problems are indeed involving two people, and they both have their goals, their objective functions, and they're optimizing their objective function. So we have two conflicting goals in general. Pareto optimality concept requires, let's say, not strictly requires, but requires several features. First of all, you should have bounded domain for the variables x1 and x2. Or if there are more variables for all the variables, you should have bounded domain. So in economic sense, it means limited resources. So you should have two conflicting and quantifiable goals. So if you can somehow quantify any loss, make it monetary, you can involve it in the objective functions, and in that case, you can come across to Pareto optimality concept. What means conflicting is more evolved topic to talk about, but this means, let me be like this. So if the point where maximum u2 and maximum u1 will be achievable, if this point is within the domain, you have no, in general, you have no conflicting goals. So if they can maximize simultaneously, so you have no conflicting goals, and you haven't, in general, you have no reason to deal with Pareto optimality concept. You can just solve the problem simultaneously, and at one point, so there would exist a point where both of these functions are maximized. And the last one, so Pareto optimality concept generally requires two or more variables. So there should be x1, x2, and even more. So this doesn't mean that these variables are indeed independent. So like bounded domain, as I mentioned, can be like x1 plus x2 is smaller than a number. So the other bounds are given by bounding the domains of x1 and x2. In that sense, they are independent, but they are somehow tied to each other by these restrictions. This was the concept of Pareto optimality. Now I would like to talk. Okay, one more thing I forgot. How we construct the Pareto optimality frontier? We fix a level of one function. So we say we desire this function a feasible level. So there should be x1 and x2 for which this is achievable, and maximize the other. So you can see, for example, if I fix here one level of U2 and maximize U1, so I will get here, and this is Pareto-optimal point. Then for another level, and so on. So for each level, I solve the problem. Also, the mirror problem also should be solved. So you can fix U level of U1 and maximize U2 and get this frontier. Initially, it was proposed in a different study by Wilfred Pareto, a famous economist of his time. But he found several uses, not only in economics, but also in many, many other situations. As far as I know, it was also applied to thermodynamics by Vardan and Sanasar Babajanyan. Also, it has uses in other aspects of general physics, if I'm not mistaken. Several papers I have read on that. However, the main idea, the main field of application still is economical. It is general microeconomics, social choice theory, and game theory, which economists deem to be their theory. But it has also a mathematical firm background, and these problems where this is crucial are called multi-objective optimization. So it is in words, it is the same when you have more than one objective function which you have to optimize. And but our concern is the bargaining problem. So let me talk a little bit on bargaining problem. What is it? Here we will talk on a bargaining problem when you have two people. But in general, bargaining problem is about splitting a given amount of money or resource between the participants. So you have a group, you have some amount of money, and you should decide how you should split this money, how you should divide this money among themselves. The one concern I should say, so that we don't take into account any sort of contribution in the gaining of this money. So it may be you have a group and someone worked very hard, the other even don't work, but they should also attribute it a little bit of this money. So we don't take into account how much they worked for that money. So that is not a concern of general bargaining problem. We have no information where this money came, where this resource came. So it is just general amount of money, and we should distribute this money among the participants. So you may argue that a fair split is fair division. So 50-50 division, for example, for two players is obvious choice. However, economic theory is mainly based on utilities, not on the money itself. So we are talking about utilities of people. So one might regard this 50% of money to be a huge amount for him, and the other may regard this to be lesser or insignificant amount of money for him. So the difference between the participants is crucial here. So we will take into account the so-called utility function, the function which they the value which they assign to this money. General bargaining problems here we'll discuss are two-player. There are two players, they negotiate on the division of this given amount. And if they come to an agreement or on a split, so the split follows. If they don't come to an agreement, so it may be regarded as a one-stage negotiation. If they don't come to the agreement, they go home with some initial amount of money or initial amount of utility, which is called defection point. So you may regard it like this. They have already some money in their pockets. So the defection point is that they will gain 0 both and go home with their amount of money, which they have initially. Two players negotiating about the amount of money, no agreement, you go home with this much of utility. Yes, this is the minimum utility you can get. You can't get smaller utility than the one mentioned here. They first attempt to solve this problem take us back to 1930s, 1925, something like this. It was the first quarter of 20th century. Although I should mention that at this part, bargaining theory was mainly devoted to strike process. So when the workers strike against employers, I will connect them later with how they are related. This mathematical formulation is like this. You have two utility functions. X1, let it be the money the first player gets. X2, let it be the money the second player gets. I'm sorry, I wrote this A. We generally write here X. I don't know why I did this mistake. So if no agreement, they go home with these utilities. Defection point represent the utilities. So there is some S domain of values of utility function. Let me go back here. So these may be the domain of utilities, achievable utilities for both. We need a rule to somehow understand how the splits will be done. We need a rule to find a point from this domain, which will be the agreement point there. The one, for example, let it be the point B. It means that the one will go with this utility, and the second one will go with this utility. I mean, do you see the cursor or no? Yes, yeah. Later, it can be translated back to money. So when at this point we are just speaking about how much utility will gain the one and how much utility will gain the second, which if fairly divided we can back translate to how much money will get the one, how much money will get the second. What is called the bargaining solution? It is assignment of point from the domain. The point should be in the domain. So we have given a domain, we have given a defection point. It should be some rule or algorithm which will find the point from this domain. And how it is a general concept of bargaining solution.
Vardan, before you proceed, so may I double check with you? So the money is in excess or is in use? So I mean, like the total amount of money is represented by use or by excess?
No, but the amount of money is excess. The amount of utility, the change of, in general, it is the change of it, but you can regard it as a utility. So the utility is it has no measuring units. So it is what we are talking about. These points have no measuring units. So they are neither dollars nor something else. They are in this sense dimensionless quantities. So
right. Okay.
X are the representing monies, the amounts of what they get.
Okay.
So how, for example, let's me bring an example. For example, this frontier, how it is found, I haven't written here, but I'll try to write here. For example, if you take square root utilities, so it is, for example, for the first player, it is x1. I'm sorry, I haven't written for a while with these tools. For the second one, of course, he gets the same utility, but for the money he gets. So let x be his money. So he will get this kind of utility. When you try to write utility at U2 as the function of U1, you should instead, I'm sorry, x1 here, x2 is what he gets. So the other amount he gets. So instead of x1, I can write u1 squared, and you will get like u2 is square root x minus u1 squared, and which you, if you draw, will be something like this. The amounts of money are somehow hidden here. We'll deal with only with the utilities. But to be fair, this is a general form of Pareto frontier.
Right. Now it's more clear, yeah, what you meant by, yeah.
It is, in some sense, if you have concave utility functions, concave in x1, you will get some sort of like this. Maybe not this symmetric, but you may get something like this. So it is decreasing function, u2 is decreasing function of u1 on a Pareto frontier. And also it must be concave also. So it is like something like this. So how do we understand what is good solution? A general solution to bargaining problem can be anything we say. So it is a choice of a point. If we can both come to this choice, that's okay. But because we speak abstractly, we want an algorithm to bring us to that point, we need some features to say that this solution is a good one. Generally, it is deemed a good solution when the solution is on Pareto frontier. Otherwise, you haven't split all the money. For example, you have you want to split $100. Each of you take $30 or $40, whatever it is, but you have $20 left. So it is not, in general, a good bargaining solution, because you could both be better off. For example, you could both take $45 or even $50 if you want, but each of you take only 40. It is a way to make each of you better off. That's why that is not deemed a good solution. But there are also other requirements. This theory entirely starts with Nash axioms and his solution. However, I would like to emphasize that the precursing ideas of this were already known to other scientists as well. But formalized and good solution was given by Nash in his paper in 1915. So what are those requirements? The first one, the requirement is symmetry, which means that if this domain is symmetric, then the solutions must coincide. So if I give no difference to labeling the players, so I mean, let me also one more time go back to here the defection point is 0. D1 is 0. If they don't agree, they go with 0. Here also D2 is 0. The maximum length here, so it is this domain is S. This domain is S. It is entirely symmetric in meaning that if I change U1 and U2, replace them by each other, change places, so geometrically it won't change. We have no change in shape of if this is the case, then the solution also must be symmetric. It means that specifically it should be 50-50 split. It is not so bad requirement, but at some point, some other scientists conclude that without this requirement, we can also come to an axiomatic solution, which is called non-symmetric Nash solution. But I will later mention about it. The second one is scale transformation invariance or covariance. They're sometimes called, or they called affine-transformation invariance or covariance. This means that as a utility don't have concrete scale, rescaling utilities will just rescale your solution. What does it mean? If we rescale the entire domain by the same A, the same multiplication and the same change of starting points, and the same we do with deflection point, the solution will just shift it in the same way. So if, for example, if we measure utilities in hundreds, if we start measuring utilities in thousands, that will just 10 times multiply our solution, and that is the case, and that is all the story about. And this is entirely acceptable requirement. So we shouldn't be bound by exact scale. Utility has no scales, and we should be free to change it. But we should be free when changing both utilities simultaneously. So if we change by the same, we change the scale of both of utility in the same way, the solution is not changed in a sense that it is changed in the same way. And two more axioms of Nash solution is that Pareto-optimality, which means that the solution should be on a Pareto frontier to be deemed as a good one. And the last, which some people find the most controversial one, however, maybe some other are also controversial. It is called independence of irrelevant alternatives. What is it about? It is about, let me state it as it is, and I will try to convince you that this is not as bad as it may sound. If you enlarge your domain, so if you enlarge your let us deem that you can do that. So you can, as you could split the $100 in the same way you can split the $1,000 if we roll back talking about money. So this will enlarge the domain of utilities, of possible utilities achievable. So if in this achievable new domain, your solution is still in previous smaller domain, then it means that the solution in previous domain should coincide with this with the solution in the new domain. Let me give an example. For example, let me draw on this. Okay, on this. For example, let us think that the previous domain were like this. For example, I mean the convex hull of these points. No, nothing more. It doesn't mean that the here is empty. So let's think that the new domain, the red one, is T, and the solution there is, for example, let us draw it in black. For example, the solution there in the red domain was this point. It is still in the domain of the smaller problem. So this means that in a small problem, the solution should be the same. So if enlarging the domain still, after enlarging the domain, if you still find the solution in previous domain, so this should be the best point in the previous domain. We can think exactly like that. We are finding a best point. If the best point of an enlarged domain is still in the smaller domain, so this point is also the best in the smaller domain. This point is better than all points here. Also, it is better in all points in the small parts and so on. So I hope you understand. If no, if I convey my ideas not so precise, let me know. I would try to elaborate a little bit more.
So maybe my question is naive, but I mean, the way you drew it, that axiom seems kind of a triviality. Could you is there an easy example where it's actually non-trivial, where you see that it can lead to something that you would have other choices too, right? That you actually have to choose.
So to just make things clear, you think it's trivial that this is a solution, you mean that, or you may argue that this should be a solution. So it's about solution that it is trivial the way I draw, or the general functions I draw make these axioms trivial.
No, yeah, the way you drew it, yes, indeed. I mean, these touching points are, of course, good because they were good, right?
That's not always the case. So let me try to draw something else. No, there should be a touching point. So otherwise, just intuitively you will have to find. So it will conflict the Pareto-optimality requirement. For example,
right.
if I drew like this, for example, the previous domain, if I drew like this, you understand that the only case where this solution in bigger domain can coincide are this point and this point. There is no other way for solution in this domain to be Pareto optimal and to be also in the previous domain. You have no other way. I draw the previous pictures just for convenience to have additional points to choose of.
I see. Okay. No, okay.
I guess this is, sorry for interrupting. I guess this is kind of a philosophical question. It's like if I am the best wrestler in the world, then automatically I am the best wrestler in my country.
Yes,
and this is kind of obvious unless there is lack of transitivity in this order relation in a sense.
Yes, the thing is that we require transitivity. It is the requirement out of the domain of these axioms. We genuinely require it for both players. So I didn't mention it, but you are right that transitivity is indeed here, and that it should not be broken in any way. However, you can, without mentioning even transitivity, with these four axioms came to the solution, to the Nash solution. But on the other hand, you are also right that this is a slight generalization of general philosophical rules that if one is best in one domain, it is the best on a smaller domain as well. So it is nothing more like it. The problem is that existence of this is not always about the best. I formulated it, but this may be misleading in a sense that if I have alternative options, I can value more the options I had. But if no, so it is like when you're comparing one option to the second, it is easier problem to solve. I mean, it is easier for our brain, it is easier to solve. But when you are comparing one option to 100 options, you may even miss a better option. So you have that energy, that time to explore all the field and understand. We ignore these problems, stating that they should coincide. But
it might be the other way around as well. Sorry, maybe it's irrelevant. But say if your utility is kind of the creativity of an artist who has applied for a competition. If you have just two artists, and then one of them has drawn something in red and the other has drawn in black, I mean, they seem quite equal, and your algorithm might choose one or another. But if there are 1,000 artists and 999 of them have drawn in black and one of them has drawn in red, then it becomes more obvious. So kind of this can go the other way around as well. So you extend the domain and it becomes more obvious, right?
I really don't understand why it becomes more obvious. It is all 1,500
because
black
the
pictures
utility,
and 1,500 red
because
pictures,
the utility was defined to be the creativity. If one person is doing black and everyone else is doing red, then creativity
everyone else
about...
is doing. Okay, I saw half is doing red, half is doing black. I saw.
No, everyone else is doing red.
Okay. Right? Okay. Yes, it works in the other direction as well. So existence of alternatives may really alter the choice. Maybe in a, but it is also somehow related to breaking transitivity in one or another way. Not entirely, but it may be related to breaking transitivity as well. Okay, let me try to continue from the last axiom here. But it is really interesting topic to talk how some scientists argued against this axiom. And there are tons of literature on that. But I think I have read a lot of them, but I think I have only few % of information that it is written about this axiom and how it is not so obvious. So if these axioms are satisfied, then Nash showed in his paper that if these are satisfied, then you are indeed the rule which this was all about rule. So one more point I forgot to say. The rule of choosing point, it seems to me obvious. For example, if S is two-dimensional, C is also two-dimensional. So it has two points. It is like vectorial. It should represent a point. It should have the same dimension as. So if C is, if the algorithm of choosing indeed satisfies these axioms, so Nash showed that you can obtain, so that your algorithm is indeed doing the following, solving the following problem. It is you like maximizing U1 minus D1, U2 minus D2, you are maximizing this. Keeping U1 and U2 on Pareto frontier. One obvious thing that you may argue is that you can always move D1 and D2, so you could also write just U1 times U2 is being maximized if I can take D1, D2 to be 0. The problem is you can't do it directly. If they are different things, you should shift them both by the same amount. So you should multiply by the same and plus or minus the same amount. If they were initially different, they can be taken both to be 0. So this is not redundant at all. You might at some point think that they are redundant because it's like scale shifting. I'm just shifting my ruler. So no, it is not redundant. At least we can take one of them 0, but not both of them if they initially were different. But in most of the cases in our application, we will take them to be both 0 because we will take the domain to be symmetric. The Nash non-symmetric solution emerged from discarding the symmetry axiom. If we don't require, so this is axiom. This does not mean that S is really symmetric. That means that if it is symmetric, this should be, the solution should, for one player should equal to the second. However, I would like to mention that discarding these axioms means entirely getting rid of these axioms, not saying that S is not symmetric. This is not discarding an axiom. Discarding an axiom means that you, even if it is symmetric, you don't have to, the algorithm should, the solution shouldn't also be like this. So the C1 shouldn't be equal to C. In that case, it was shown that that sort of solutions are in a form like this. So U1 minus D1 in some weight, these are called weights of the players, weights of each player, or weight of each goal. So it is so you are solving this problem instead of this when you discard a utility symmetry axiom. Okay, this is I really can't show easy way how you can derive this in 3 or 4 minutes. That's why I didn't include the proof that you are indeed solving this problem. But this is the point up to which we use this whole information and propose our method of solving bargaining problem. So what we did was based on Weber-Fechner law, or more precisely, we see that we are entirely using only Weber law, no Fechner law. Weber-Fechner law is famous psychophysical law, which states that to perceive a change in stimuli in some source, for example, when you are lifting some weight, to perceive a change in this weight, it should be proportional to the initial weight. It should be proportional to the initial signal. For example, if you are lifting 10 kilograms and I add 1 kilogram, you will see the difference. But maybe if you are lifting 100 kilograms, 1 kilogram you may remain unnoticed. I'm exaggerating a little, but this is the case. So there should be some constant according to Weber law, after which you start perceiving change. So this is the minimum change required for the subject to understand that there is a change in stimuli.
So sorry, is it another way of saying that a human perceives change only if that change is exponential?
It is addition of Fechner law. It means that yes, if you try to solve this, you can come to logarithmic law, and yes, the change it is sort of exponential.
So any growth slower than exponential, humans don't perceive as growth.
Initially, Weber's law was about that, but later it was shown that it is bound to errors in for example, for small weights and very big weights. It's not about only weightlifting. It's about, for example, a change in intensity of voice, a change of intensity of light, and so on. So when there are too small amounts of weight, this law is not the same way it is written. But initially, yes, initially it was like this. But on the margins, on the extreme values of stimuli, it a little bit changes. But yes, this means that of course it should be proportional to initial weight, which means exponential law, yes, power law. Not the power law, I was wrong, in an exponential form. So, but Fechner additionally said that chi is different for different people, and also for different physical quantities measured. We tried to use this law to understand how a bargaining process can be conducted. So how we use this law? For example, let me bring an example on talking about money. So when you have, for example, $1,000 in your pocket, losing 50 cents isn't a big problem. But when you have only $5 in your pockets, losing 50 cents is a problem. So a change, we doesn't say that you will not notice this change, but you will reluctant to argue against this change. So, for example, if the bargaining problem is about pulling to your side an amount of money. For example, if the first player tries to split like 60-40, you can try to symmetrically say that you want 60% to yourself, 40% for him. So it is about pooling. And of course, there may be some small domain when you are indifferent if this amount goes to him or you. So there is a small margin when you are indifferent. Of course, it depends on the real amount of money we are talking about. But we, and here what I'm talking is about real amount of money, but we use this Weber law to utilities. So we perceive changes in utility rather than perceive changes in money. So there is some interval when we don't mind if he takes this small amount of utility to himself or it is given to you. You don't mind. That doesn't mean you don't notice it, but you don't mind of this change. So in this way, the bargaining problem could be formulated like this. Let me shift to general way of saying it. So the first player is trying to maximize his utility, which he can gain, in a sense that a small amount of change which he will perceive, K1 is his constant, he should perceive this change, will not be argued by the second player. So what is the hash function? Hash function is, let me go back again. This is hash function. For example, if we are able to represent dependence of U2 of U1 by a function, and which is the case generally, we call it the hash function. So the inverse of hash function will be G function, which will show what. So he is trying. So generally, it means that hash is representing the value of U2. So the change in the second player's utility over, I mean, absolute value of change over his utility at the point, he should not argue against this change. And you should also perceive this change to go to commit the change. I mean, we maximize U1 up to the point where you can do one more step and no more. So what does it mean? Let me be more clear. So you are trying to have as much utility as you can in a way that when you try to change a utility, you can really change a utility one more step, one more time, which you will notice. He will not notice, or he will not argue against it. But as we maximize U1, any further step is already impossible. Would you agree with me or disagree? I would like to, if I stated something not clear, I would like to make it more precise.
That sounds okay, I would say.
I
So
mean,
it's like a redistribution of wealth problem. Like everyone pays taxes, and you slightly redistribute. You tax the rich people more, and then give some of this money as kind of support to the poor. And if they don't mind, then it's
yes,
good.
it is. Yes, it is. In don't mind setting, yes, it is like it is easier to take small amount of money of several people's than taking the same amount of money from one people, the cumulative amount of money from one people. But here in this setting, he is not taxing, he is just pulling to himself at the point when the further pull is either impossible in a sense that he will argue, he will disagree, and you will go home with the defection point with zeros. Or you can pull a little bit more, but you will slightly perceive it and no more. So it may be even written equality here. So I am pushing to the moment after which I can't make any changes because he will argue. So we took, for simplicity here, deflection point to be 0, 0. So if we write this for both players, it is written like this. But I was wrong here. Sorry, I was wrong here. There should be G function here. I copy pasted the same. I'm so sorry. There I will. This should be G function. And this should be U2s and 2. I'm so sorry, I just copy pasted the one. But the idea is that this is the first player's problem, and the second player's problem is similar in a sense that he just do the same thing for him. He tries to maximize his utility. But with the same, he will notice and the other wouldn't argue. This is the case.
So this is a definition of Pareto optimality in this changed scenario. Is that what it is?
Not entirely, because we could be on a non-Pareto optimal point at the moment. However, we require this Pareto optimality. So here, let me go back. Here we require this Pareto optimality. In other way, we require this Pareto optimality to be exactly the function which was like this. So we require this Pareto optimality. We could be like here, and in that case, changes could be huge. This change, for example, up to here from the second player can be huge and still unarguable by the first player. So they are pushing themselves up to the Pareto optimal, and then we use the Weber's law. Otherwise, I can't say if he takes U1, then the second one has HU1 utility.
Right. No, I'm just trying to understand. So if I take K1 and K2 to be 0, I mean, in which sense do I go back to the previous problem?
No, okay, that's a good question. K1 and K2 can't be 0. They can be any positive constant very close to 0, but they can't be 0.
Because you will never have this smaller or equal than K2 thing to have a meaning.
Yes, this is, you can have only when this change is exactly 0.
Right.
And this is the same for here. So now we try to avoid, of course, and initially Weber law required this K to be positive constant. However, our results is indeed where we are too sensitive. So this K1 and K2 shows, in a sense, our sensitivity towards the changes. If we are too sensitive and we are going to analyze this, the following results are true. So if we have K1 equal to K2 and they are very small, so we try to make them go to 0. Then the solution exactly coincides with Nash solution. So if we solve the same problem for both of them, this is exactly the Nash solution. So in that sense, Nash solution can be regarded as a special case of Weber law-based bargaining solution. However, when there is another interesting consequence of this is that if K1 is not equal K2, but their proportion is fixed and they both maintaining this proportion goes to 0, becomes smaller, the solution goes to non-symmetric Nash solution. I know I wrote coincides, but it means converge to Nash solution. If being enough small means coincides with. So we can achieve both symmetric and non-symmetric Nash solution with these two additional constants and formulating this with Weber law. But also we find another consequence of Weber's law, applying Weber's law to this bargaining problem, is that whenever you don't do this last step, you are taking this amount of utility, and whenever you take these last steps, you do this amount. You take this amount of utility. And the problem is when you deal with bargaining problems, it is the case when K1 and K2 is not so small and you will not converge to a point. So you will not take an exact point solution. Let me be more clear here. Now let me roll back to this graph. I'm sorry, I should have taken it so. So whenever K1 and K2 is small, the one will solve at this level of U2, the first one may solve at this level of U1, and they will coincide really. This may be either exact Nash solution, or this may be other point which is non-symmetric Nash solution. But if K1 and K2 are not so small, are not small enough, then the first one may take this level of utility, and the second one may take, for example, this level of utility. So they will stop at this point. Yes. In that case, you haven't solved the problem entirely. You have just made one step, but you haven't solved the problem. You haven't split the money entirely. But we found that this opens doors for iterative solutions. So after this, you can cut off. This is not the same. I will argue that this is not the same. But you can cut off and make the same solution for this part, and after which again and again, and somehow you will converge to some solution. After infinite steps, you will find some point here like this. But even in that case, that must not be Nash solution or even non-symmetric Nash solution. It can be entirely other solution. So in this problem, when we solve it iteratively, the final solution, the final point where we converge, has not to be Nash solution at all. It is close. It is indeed close to Nash solution and non-symmetric Nash solution when K1 and K2 differs, but it has nothing to do. When solving the problems formulated in a Weber law, we really come to an interval. This is with final step, and this is without final step. So when you take the final step, if both of you take the final step, you won't come to an agreement. So if you both take the final step, you will require more than the last step. So let me be clear one more time. I will roll back here. So to show you again one more time this. So let this be level required, let this be level required. So when you, for example, when the second player did the last step, he will require this much. I'm sorry, the first player, he will require this much of utility, which is not acceptable for the second player because he requires this level. It is lower than the level he required. So if you if you commit this last step, and the second one the same way can commit the last step, you will not meet an agreement. Well, if you avoid doing this last step, you have an agreement point here, and you can go further, continue bargaining on the remaining amount of money. In other words, when you start bargaining, you can initially say, let, for example, 40% be mine, 40% be yours, and for the remaining 20%, we will continue bargaining. It is like in a negotiation process in politics. So whenever we are okay for the counterpart to take the part of this money or anything else we are bargaining about, it's okay. We can try to later negotiate on the remaining, which we weren't ready to get to give off to the second player. So it is entirely the same as in the politics when you converge to solution it is so-called bottom-up setting, so bottom to top setting. You may argue that bargaining process, and it is one way of conducting this bargaining process, is at first committing larger goals and then to concede to come to an agreement. But there is another way. You can gradually come closer by gradually splitting this amount to smaller groups and taking to smaller parts and taking each. So we proved that that this was the last, pretty much the last result, that when you do commit the last step, you won't come to agreement. So this inequality exactly shows that. If you don't, he requires less than you are ready to give him, and you require less than he is ready to give you. But when you commit this, you give him less than he wants, and he gives you less than you want if you both commit this last step. So we argue that you shouldn't take these last steps and continue bargaining on the remaining amount. So this was all I would like. These were all results. We have a smaller results on ultimatum game, but I think I have already used more time than I was allotted. So thank you very much, and I'm ready to hear all of your questions and anything you want.
So, I mean, I guess one global question is that I think you went too quickly with the last result, and I would actually like a repetition because I didn't capture most of it.
The last result was, let me again repeat the same with simpler words. U1 star is the amount of utility you want for yourself. Let us be the first player. I want for myself this amount of utility, and this is the least I am ready to take, but I can want a little bit more if I commit the last step. So this is so when solving this problem, you really have two variables. You find two variables. The first one is U1 star, which is the solution of the problem. The second one is delta U1 star, which is found by in the steps of solving this problem. It is entirely that you are equating to K1, and delta U1 star is exactly K1 times U1 star. So the solution is like that. What this means? This means that you can take U1 star and be enough, but you can also make U1 star plus this delta U1 star, and you will notice this change. The second player won't argue in general to this. However, this means in this case we haven't solved the second from the second player's perspective, so it is only the first player's problem solved. But you can either do the last step, make the last step, or you can avoid doing it. So when you don't take this last step, you take this amount of utility. When you take the last step, you take this amount of utility. This is still non-arguable from your idea, from your information about second players, and it really indeed is not argued. The same is for the second player. However, when solving for both players, these intervals overlap. In what sense? In the sense which is written here. So it means that if I require this amount of utility, but he didn't commit the last step, he is ready to give me this utility because he required this much, and G was the hash minus 1, so it is what the inverse function. So it is representing my utility, which I will gain if he take this utility. Right. So in some sense, it is the utility this is the utility he is ready to give me, so to give off to me. So this means that if he doesn't require the last step, don't take the last step, he is ready to give me even more than I am expecting. So that while if he really strictly required the last, took the last step, he will be ready to give me less amount of utility that I will require. And the same is for me giving some amount of utility to him. If I really do take the last step, I'm ready to give off him less utility than was his solution of his problem. So in that case, we won't meet. So we will, let me draw it one more time. So if the situation is like this, we meet at some point. If the situation is like this, we never meet. So if I require more than, and in that case, he will get less than his threshold, he will argue against it and we will go home. And the same for me. If I took the last step, this will, if he took the last step, he will push the line to here and we will not meet, because in that case, I would take lesser amount of utility than I would require. Then this is my threshold. So.
Right. So basically, there is some kind of an asymmetry in your definition of this Weber's law, right? Because if this delta U1 and delta U1 and U2 are fairly small, then in principle, I mean, the very fact that you said that you have a lower bound, that means that at some point your sensitivity is kind of rigid. You can go up, but you cannot go down, right?
It is no reasonable to go down. I mean,
I mean, you typically write it with an absolute value, so you
yes, yes, your argument is exactly correct. But I mean, when you are maximizing, you are trying. It also requires to delta U1 to be positive. We just showed that it is possible to maintain positive. So it's. Yes, we here we omitted this we didn't do it in absolute value. Here we should also have omitted, but in general it will yield the same solution. So there is no reason to go backward.
But you all the while you remain slightly insensitive even to
yes,
slightly
yes,
negative
exactly.
delta U's.
Yes.
There is always rooms for going lower.
Yes, you can go smaller changes, but he will not argue against smaller changes. But in that case, you will not perceive that changes. You may argue why I did take even. You can think economically and say, I will take as much as I can, even if I don't perceive the change. I will push to the bound. So the more the better, even if that gives me not. So you can fight for each cent, but so when you take this last step, it means you are trying to fight to gain as much as you can. If you are not taking these steps, it means you are insensitive to intermediate changes, smaller changes. You need a big step to perceive it, but this big step will become arguable by second class. He will not agree to this change. So the bigger you want, the bigger changes you need to perceive these changes. Yes. But the bigger changes will be not accepted by second player. So pushing U1, push delta U1, but to have both of these inequalities satisfied, you can come to a solution, to an optimal solution.
Fair enough. Very good. So do we have any more questions from the audience?
So say the first kind of phase of the algorithm terminated at a certain step where the next step is not possible because either of the players will argue, right? And then you say
it's possible, but it is marginal in the sense that you will have equality here. You will exactly perceive this change, but no, the solution is U1 star, which is one step back. You can still do one more step, if I got the question right. Yeah, no, you can do one more step, but it is not always reasonable to do. When you are
right. So but you terminate it there and you say from this point on, let's begin a new phase of negotiations to run the algorithm again. So do I understand correctly that in the new iteration, you need to change the coefficients K1 and K2 to make yourself more sensitive?
Yeah, no, that was my mistake. I thought I have few amount of time and I didn't talk a little bit about this iterative bargaining phase. When you terminate on the first phase, so you come to, for example, this agreement. So each of you take the mentioned amount of utility. So you came to this point, and each of you take the sum amount of utility, and the second player his amount of utility. After which you should calculate how much money each of you took. So you must roll back to the money formulation of the problem. You should calculate, for example, if we are splitting $100, this may mean that each of us take $40. And the next step is new step when we are bargaining already on $20.
So basically, upon each iteration, you update the D. Is that correct?
In some sense, yes, but you can alternatively formulate it like you update the general amount of money, the X. The whole amount of money is getting less.
Right. Yeah, that's a fair point, yes.
So, I mean, I'm sorry. So how does just the next step in the single phase differ from the switch to the next phase?
So
because in the single phase, like the algorithm, on every next step with these deltas, you are doing the same, like
exactly the same. Exactly the same, but different Pareto frontier. For example, new Pareto frontier would be like this. So the same arguments, but like this.
It's just one piece of the old one, right? So again, we are kind of it's just a subdomain.
It may be regarded like this. It's very similar. It's not exactly the subdomain because you have to reconstruct this domain on having new amount of money. But you took off already this utility. So as Karen mentioned, it is like changing defection points. With new defection points, let me roll back there. Maybe I missed something. Or in general, here we have take defection points to 0. So if we don't take this to 0, this should be written like this. It should be U1 minus D1, and here HU1 minus D2. So suppose that you solve the same problem, but with different defection points. With different defect, it is already a different problem. Slightly, but yes, you are doing the same procedure, but it is a little bit different problem.
So you're saying this Weber's law of logarithmic growth, it is with respect to the amount which you already agreed to take rather than the amount that you have.
Yes, it is only about gained utility. In the problem, gained utility.
So what you had before negotiation doesn't matter if you are a billionaire or you live in trash.
For
it's
example,
the same. It's just
yes. That is a good point. Exactly. In most literature, they just only slightly mention this point, but it is the case. So we are talking about changes of our utility, newly gained utilities, not the old one. That's what the old ones are in D1 and D2, so we may subtract them from the U1 can be regarded as the whole utility, but in that case you should subtract the other utility you had already before the problem formulated.
So it's like we forget what happened in Las Vegas.
Yeah.
Now we begin from 0. Yeah.
Okay. Yes, exactly like that.
Well, if you're a billionaire, then for you the K can be somewhat what it should it be then.
It's a hard question. We haven't empirically studied it, but we had a talk with our colleague, which also worked in different firm. So we were talking to her. We asked her to ask her colleagues about how would they perceive if their salary would be changed, for example, for 5%, 10%. At what point of time they will start to argue? Argue means that they will drop off their work and go to find other work. So most of them said that these cases are too small. They even 1% of change of their salary will make them change their jobs. So I can't exactly say what is what amount, what is the magnitude of K1 and K2, but it is from most possibly from 0.01 to about 20%, because these can also be found when I am not sure if you know, but there is a strategy when supermarkets indeed use this Weber law. They slightly change the price. They gradually increase the price as much as you won't even either you won't notice or you won't be against of this change. So in some studies, it was shown that up to 10 or 20%, maybe you would have some inconvenience, but you will still continue to buy that product if it has no good good alternative.
Well, I mean, my point was that, I mean, if you already have a lot of money, then for you the threshold can be somewhat, higher, right? You wouldn't care much.
Yes,
so that could be encoded in K1s, the prior.
Yes, indeed
weakness.
It can. Indeed it can. We haven't addressed this question, but we do understand to acknowledge that this is possible. That K1 depends on your initial wealth, so or initial utility.
So in principle, if you're running an algorithm, then in principle you could update the case also from iteration to iteration, right? I mean,
yes, if we think that this amount was that influential for them, of course we can alter this K1 and K2. However, there is also an evidence which says that rich people are even more sensitive than the poor people. That's why they are rich. It is argued like that. So we are not sure what is the connection. So what form of dependence is K and the initial wealth? It may differ from a person to person, but generally we perceive that there must or should be some kind of dependence on their initial wealth.
Right. Very good.
But we haven't modeled this yet. We haven't.
Yes, let's call high tolerance spiritual wealth, right? So. Okay, do we have any more questions in the audience?
So one thing that comes to mind, I mean, I understand that maybe it was your goal to kind of concentrate more on the algorithm rather than on the final state. But well, Nash's result is not constructive. It just says, well, there exists a state. So it's like the existence of a final state, which is optimal in one sense or another, say the same Weber's law. But what you do is like you suggest an algorithm for getting there, and this algorithm is discrete, kind of discrete steps. It is kind of well suited for computational and applied purposes. But from a theoretician's point of view, like me, I like continuous processes more, and I like kind of optimization problems like Lagrangian formulations and so on. So could you perhaps make this more continuous, more mathematical in a sense?
This is indeed an optimization problem. So it is not out of your interest. So it is an optimization problem. It is not that kind of continuous optimization problem, but it can in most of the cases when K1 and K2 are enough small, it is indeed an optimization problem, which has shown to be the same as Nash solutions. The one thing is that, yes, in the paper, we also argued that Nash solution is not constructive. So there are attempts to make Nash solution to make steps how the Nash solution can be indeed obtained, but in 3 or more papers which is devoted to this topic, the main papers we have read, this requires additional person, an external arbiter who will make these people to go to not commit some steps, to not take some steps against. So it requires external arbiter, a third person. In our case, there is only 2 things you should know: your sensitivity, the sensitivity of the counterpart, and that's all. Of course, with you don't even have to take this into account. I mean, the H function is not generally the case. You can just solve. I mean, let me be clear. So you can have his utility, but you can have your Pareto frontier, and so you can have no information of his utility, because several utilities can give the same Pareto frontier. But what you said you are more interested in what kind of problem. So it's constructive, but if you are interested in convergence properties, we weren't able to address this question. So in iterative bargaining, when you have infinite number of steps, we don't know where it converges. It is somewhere close to Nash solution, but a non-symmetric Nash solution, but it's not entirely.
So you can't describe the endpoint somehow by some optimization.
For some function, we can explicitly say that this is this. But
yeah, no, I mean generally from some principles like.
No, we weren't able to Yes, there is some principle, of course, and unfortunately, I have a paper with me on this computer, but there is some entirely. It can be shown to be a series. So the split is the infinite sum of small amounts, and we can describe this infinite sum. But we can, in general case, we couldn't have a closed form solution to the utility, how much one gets.
Or like write maybe complicated, but still somehow like write Lagrangian, if you wish, and say, well, the point where this algorithm converges is the minimum of this Lagrangian, and we can't compute it explicitly, but it is.
No, we have series. Sorry. We have exact form of infinite sum. So each term, we know each term of it. We just don't know where it goes. So it, in a sense, if we accept this as a closed form solution, we have this closed form solution. In each step, we know what amount of utility and what amount of money he will take, and we will sum this amount of money, and we have the closed form of this sum, of this infinite sum, but we don't know.
But that's for particular functions, right? So not
yes,
generally.
Yes.
Not
yes,
generally.
but you can do it generally. But it will not obviously dependent on. There is no obvious formula of dependence of your utility form. We did it for power utilities like the square root of x1. We did it for logarithmic utilities. These are sets of utilities which are generally used. We can do it for several other utilities, but for general utility, yes, we can't say where it converges.
So if I understand correctly, Girard is kind of asking for a variational principle that
Indeed.
you could cast this in form of, you know.
Perhaps yes, but we weren't thinking of it in that way. We were thinking of it purely psychologically. That means we haven't found. I mean, this problem didn't arise from these results. Initially we were even looking for other results, but we saw that surprisingly it coincides with Nash solution. So we formulated it not even looking for a good solution. We were just trying to find how this behavior can be described. That's all. So where it will take us. We weren't, at least we weren't looking for variational principle.
So to make the problem more geometrical, what if I replace your discrete kind of a sequence of points by continuous curve? Okay, time-dependent algorithm, continuous. Yeah, so and then instead of, yeah, exactly. You say derivatives are bounded and then make it an analysis and geometry problem rather than a discrete mathematics problem.
Yes, for K1 and K2 equal, this is this means that the solution should be at some at a 45% tangent line. I mean, it means that it should be at the point where, for example, if it is the B point.
Yeah. So
it means
backslash tangent.
The tangent line, the tangent line is exactly 45% degree.
Yeah.
45 degree, not percent. But if K1 and K2 aren't equal, that doesn't mean anything. So that doesn't mean that should be K1 over K2. Nothing like that.
Okay, so
it may be argued that this can be taken to this form, geometric form, and there is some geometric intuition behind it. But you can one way you can think of it is that each of you is pulling this point, and you have changing velocities of this. So the further you pull, the harder it becomes to pull, and he does the same.
So maybe
If
these
you
inequalities
translate-
that you wrote for a discrete step, you could maybe write as a differential equation which the curve must satisfy, right? Or differential inequalities.
Not entirely. This is true when K1 and K2 are too small. This isn't true in general. So
why? I mean, I just write differential inequalities. U1 derivative is larger than K1, and U2 derivative is smaller than K2 or greater than minus K2. And this is a system of differential inequalities, and I'm looking for a solution. So what's wrong with that?
And what do you understand by the du1? What is the
So it is a derivative of u with respect to the parameter t, which describes the evolution.
But we haven't introduced the parameter of t.
So I'm suggesting to introduce it.
Yes,
right?
yes,
So
yes. If you translate it to more physical problem, you can do it like the way I said. So you can think of it like velocities and so on. Yes, you can. Maybe you can do this in that way. However, for a smooth enough function, could you be able to find any form of solution which satisfies this both?
yeah, I
I'm not
mean,
sure.
I'm more concerned that there wouldn't be a unique solution because, I mean, if K1 and K2 leave any room for any solution, and if then there might be an infinite number of solutions, which is maybe not bad because the efficient frontier is an infinite set anyway.
Yes,
but I don't see why.
You mean we can have this form of solution? For example, this small part of the domain may be entire solution. Each of these can be perceived as a solution.
So you can have kind of a neighborhood of flows so that every curve with its tangent in the flow satisfies the problem, say non-uniqueness, but in a constructive way. And I mean, why not consider it? The question is why don't mathematicians consider such problems?
Mathematicians may consider these problems and may are entirely interested in it, but the people who are going to publish this problem would argue that it is too evolved. I mean, the economists wouldn't take it to be either we should give a good explanation for that, or they will argue against it. So it should be kept as simple as you can.
I don't see the point. I mean, there are many branches of sciences where naturally discrete processes are idealized to continuous processes, and this allows for a lot of mathematical machinery. I don't see why this shouldn't be applied in this case.
But you should explain this how it is done in general. So whenever you have decision-making problem, maybe 99% of problems are taken to be discrete, not continuous. So when we are talking about lotteries, we don't talk about the lotteries which give a continuum of values. When we are talking about decision rules, we always deal with some discrete random variables and so on. So decision-making problems are reluctant to talk about things that are arguably infinite. So, of course, in general, a Nash solution was also in an infinite setting, in the continuous setting, I'm sorry, because this set is taken to be continuous. But you can argue that you can't have smaller amount of change than, for example, 1 cent. It is not feasible. So it is, yes, it is already idealized version of discrete problem. But to motivate that this problem should be described by a differential equation, this does indeed mean that you should take Weber's law as not a discrete law, but a continuous law. In Weber's law initially, and even after that, it is discrete law. It is not about small changes. It is about big enough changes that would be perceived. here we should a little bit at least argue why we took to be these changes that small that we can talk about differentials. If the main argument we brought there, we tried it. We brought there that k it may be too small, and that's why we can regard it as a small change. But in general, Weber's law is about exactly jump-like processes, not about small changes.
Yeah, but I mean, that's pretty much like saying, I mean, in computer science, you have these optimization problems, right? You know for sure, and following your logic, then computer scientists would say, well, ultimately, I'm going to write this program on a computer which has bits and discrete things. So your derivatives and all these Lagrange multipliers are irrelevant because I'm going to be discrete. Why are you doing that, right?
No, I didn't see anything even close what you said.
Yeah,
I
you are
said it
saying
is
because if the final application is discrete,
No.
then continuous models are irrelevant.
No, I didn't say that. I mean that we should somehow convince ourselves that Weber's law can be made a differential law. But Fechner tried to make it a differential law, but he connected it to other quantities. Well, if I would be the one reading the paper, I would for sure point out that you forcefully made it a differential law while it can't be differential law. It's not about application. It's about the entire nature of the problem. So it's not the final goal is discretizing. I can solve it continuously and then take discrete form, discretize it at any moment I want. But entirely this law is based initially, and it is only understandable in a discrete framework when you have a good change in a signal, a fair amount of change in a signal. You can't talk about very small changes without saying that k are also small. I mean, for another part of decision-making problems, when I say decision-making problems are dealing with discrete, it's entirely discrete. It has no continuous analogs in any way. You can concoct something like you can deal with continuous random variables, but generally it is about lotteries, and continuous random variables are step further and may distort the final conclusions.
I don't see how it could distort. Sorry, I mean, if you look at Weber's law, delta S over S squared equal to K, I rewrite this as S logarithm S derivative greater or equal to K, which basically means delta S over S greater or equal to K times delta T. So if you want to recover your big jumps, just take delta T large enough, and from the continuous model, you will exactly recover your discrete one. I'm just saying, well, if you want to follow big jumps, just take time kind of discreteness large enough, and you will have your big jumps. That's
so you say every signal is perceived logarithmically. So I mean,
yeah,
US, and what you come to by stating this, what you are giving to the reader.
I'm saying that if you want your original Weber's law for discrete case, just take the time points.
I don't understand why I should do that.
I mean, because this way I can derive more results, and that way you can't. That's why.
Oh, that's far from truth. That's far from truth. Most of discrete models are more precise than continuous models.
Oh, come on.
When you deal with continuous models, you can come to controversial results which are not in line with discrete results.
Okay, I'm not an expert in discrete models, but anyway, let's disagree on this point.
Okay.
Yes, I suppose this is a good point to end the formal part if we have no more comments or questions from the audience, and we can conclude the official part of the seminar, I suppose.